this is equipment failure, not me. Okay, so cloud monitoring. Is this really? Okay, good. So cloud monitoring. We build the telemetry and alerting platform for Netflix to gain operational insight into our environment. We like to say that we build ridiculously powerful systems, and then sometimes after we've built them and deployed them and made our customers use them, we even make them slightly easier to use. So a quick word about Netflix. Some of the stuff you probably already know about. How many people here know about Netflix, like what we do and all of that? Oh, good. So we've been around for 16 years. We've got about 2,000 employees. We just hit 40 million users in the last quarter. And actually, this is the number I'm really proud of, 5 billion streaming hours in the last quarter. Based on your typical life expectancy in the US, that means about 7,300 lifetimes of entertainment streamed in the last quarter, which is just an awesome number. We run things a little differently from a culture perspective than most other companies. We tend to optimize for speed of innovation first. We try to constrain availability, and then cost tends to be sort of whatever cost ends up being. That means that typically we hire smart, experienced people, and we get out of their way. I have an engineer I work with who recently completely overhauled our alerting system based on a one-sentence request from me about what she should do, and then she went and just did it all the way she intended it, completely differently from how I would have expected it or had told her to do it if I had to tell her how to do it. And we find that when that happens, it's just magical. It's awesome. It tends to be much better than if you have managers actually telling people what to do. And we, generally speaking, have an anti-process bias. Now, that's one of those sort of things that I want to be a little more precise on. It's not that we hate process. As an HR person at Netflix that I work with once said, it's not that we hate process, it's that we hate stupid process. And the nice thing about Netflix is that you can think of it as sort of like a natural selection for processes, in effect. Because processes are actually optional. You can do whatever the heck you want, and if you want to follow a process, you will, and if you don't, you won't. Which means that if any process that lasts for a while at Netflix has to be good, because otherwise people just wouldn't follow it. That's a very different approach from a lot of other companies, and a lot of other companies, frankly, that I've worked at. From a tech ops perspective, we are running a service-oriented architecture in Amazon. We have 500 to 600 different services running in each of the regions we operate in. And we follow a decentralized ops model. That means that if you're a developer, you get to write code, of course, because it would be boring otherwise. But you also get to build your code, and you get to test your code, and you get to deploy your code. And you get to figure out what alerts make sense and what dashboards you'd like to look at. And when your stuff breaks at 2 o'clock in the morning, you're going to get woken up by PagerDuty. Now, technically, it may not be you. It may be your coworker who's sitting in the cube next to you. And they might not like you so much that after that happens a few times. And we tend to find out that making it the developer's problem to support their code and operations tends to avoid some cost externalities and drive for better code and better operations. We are AWS-based for 100% of streaming, and we've had a huge expansion over the last few years. Customers, I just mentioned that we've hit 40 million customers. When I joined Netflix in 2009, I remember we were talking in sort of hushed tones, doing these sort of like, thought exercises about what would Netflix need to look like one day in the far future when we hit 40 million customers. We thought it would be like around 2018, 2019. We thought we'd have to be like a completely different company, and in many respects we have, but we also hit the 40 million mark about 5 years earlier than we expected back then. We've also expanded into a bunch of new markets. Again, when I joined Netflix, we were serving the US. We were serving all the US and just the US. These days, we're US, Canada, South America, Central America, a whole bunch of Europe, the Scandinavian countries. We're all over the place. We're in 43, 45 countries, something like that. And our metrics have grown like crazy. I'm going to talk about metrics growth in just a few minutes. Before we get into the monitoring system that we built, I want to talk a little about the monitoring system we had in the old days. Our old alerting system was actually an enterprise IT alerting system, like, a packaged software product that cost, I don't know, a bunch of hundreds of thousands of dollars. I will refrain from mentioning their name. It was managed by our enterprise IT alerting people, which, if any of you have ever had to work in that kind of environment, meant that every time you wanted to set up or change an alert, you filed a ticket. And typically, alerts went to the NOC. So anybody worked in that environment ever before? Yeah. So this sets up some interesting problems. I remember, for example, when one of our software development teams set up an alert condition that had a horrible false positive rate, like hundreds of false positives every day. And I was talking to the NOC because I was in IT and pretty close to the NOC, and the NOC was just close to crying. And they talked to the software development team, which was like super, sorry about it. And as soon as they finished working on a bunch of features, they were going to work to modify those alerts like a week or two down the road because they weren't feeling the pain of those false positives. So cost externalities for the lose. The other problem is that we had this alerting system, and it was completely separate from our telemetry system, which creates some interesting problems. So telemetry. Our old telemetry system was actually originally built as a spare time effort by one sysadmin who decided that he could do better than this enterprise IT solution. He was, in many respects, right. It was actually loved by developers. It was great, right, because developers could basically instrument their code to their heart's content and send however many dozens or hundreds of metrics into his system and then be able to easily see their data. He used a custom TCP protocol, and I'm torn between thinking that's because back then REST was only starting out as a best practice and thinking that, he just thought that custom TCP protocols are cool. And it used RRD file backend storage. So how many people here are familiar with RRD? Okay, enough that I'm not going to get into it, but afterwards, if you have any questions, find me or any of the other people around who raised their hands. And it was written mostly in Perl. It was data center bound, and it was limited by data center resources, which meant that it was starting to have problems under our metric load. And that's the second time I've mentioned metric load. So this is number of metrics in the monitoring system that we were dealing with. Right around September of 2011, we started thinking about writing our new system, because what we saw was this is in millions of metrics. We had 2 million metrics in the system in May of 2011, then 2.5 in August of 2011, which is not really that huge of a growth. That's only like 25%, no problem. And then a month later, we had a 400% increase in metrics, which, if you're running a monitoring system, can get you a little grumpy. And then pretty quickly after that, we ended up with 10 million, 15 million metrics, and red on black is hard to see, but that's about 18 million metrics. So around September, when we started talking about our new monitoring system, we saw this curve, and we figured that we really needed to come up with something that was going to support us up to, like, I don't know, 100 million metrics. More on that later. So metrics growth, right? Like, we've grown in customers, we had more systems. It makes sense for us to grow to some degree. But here's the thing. If you took our customer base and grew it at the same rate that we were growing metrics, every single person on the face of this planet would be a Netflix subscriber twice. I wouldn't mind that, but that's not what's happened so far. It also means that if our penetration on smartphones was this good, every single smartphone on the face of this planet would be running 10 Netflix clients. And nobody would like that. So clearly, our metrics have grown at a rate that is disproportional to pretty much every other KPI in our environment. So this was a problem. So we decided to build something better. A few words about what we built. We started by knowing that it was going to take us a while to migrate from our old metric system, Epic, to our new metric system, Atlas. So we built a UI that could transparently get data from either of these two systems. So you didn't have to worry about going to one system if your metrics were there, or another system if your metrics were there. While we were at it, we also figured we might as well throw CloudWatch in there. So we've created basically a multi-system UI that automatically gets your metrics from wherever the heck they are based on what metric names you're asking for. We built this thing from the ground up for regional isolation. So metrics stay within the region in which they were collected. It's very easy to get region-specific metrics, but we also have global endpoints, so you can get multi-region metrics. We had an interesting problem before about figuring out what a given instance belonged to in terms of an application. So the way it would work was an instance would send us some metrics, and then we would use a whole bunch of inference on Amazon's ecosystem to figure out that, oh, that instance belongs to like the Bob application. And that inference was done by a system that occasionally would have problems, would miscategorize instances, and suddenly a whole bunch of metrics would get categorized as belonging to a completely different application, which would have alarms go off and a whole lot of people being confused, and that made us sad. So we built our client for this new system. It's called Servo. It's actually open source. I urge you to check it out. And the client now actually sends in with metrics the identity of the server and what application it belongs to. In fact, I'll get to that in the next slide. That's made our metrics actually much more reliable. And we've seen basically no metric drops since that, we've made this change. So what's a metric, right? And actually, more importantly, what's a metric name? Well, here's a metric name. For those in the back, can you read that? Here, I'll make this easier and I'll read this for you. com.netflix.eds.successful.requests.uiversion.nccprt.authorization. One second. Dev type ID -101.clver phl_0ab.uiver-ui_169_mid.geo-us. Okay, who's seen metric names like this? Yeah, so everybody tries to put a whole bunch of metadata into their metrics so they can do later, like, slicing and dicing of their metrics, and in the end you end up with metric names like this. And you know that you have that problem, by the way, if you run a monitoring system and your customers, like developer groups, go, hey, your 256 character limitation on metric names is just too short. We need longer metric names. That way lies insanity. So here's what we decided. We decided that metric names are not actually a vector of characters. Metric names are a list of key value pairs. Here's what that looks like. So here's a key value pair. NF, Netflix.ami is AMI-AA5166EF. NF.app is WP for white pages, one of my personal applications, actually. NF cluster is WP batch. NF ASG is WP batch-V163. ASG is for autoscaling group. NF country is US. NF node is that. NF region, NF zone. The reason these keys are bolded is because our telemetry client, Servo, it's open source, check it out, actually sends them in for you. So you don't have to worry about sending these key value pairs into our system. We'll take care of that for you. And then you as a developer get to figure out what a reasonable way of representing your data is. So for example, the above long string could be represented as a set of key value pairs that are class NCCP, type request, UI version, whatever, action, authorization, dev type 101, CLver, PHL0AB, and GeoUS. And we've made it exceedingly easy to slice and dice based on these key value pairs. In fact, speaking of slicing and dicing, let's talk about the query language for this system. Who recognizes this thing? Okay, we're all old. So this is the HP 28S. It's one of my favorite calculators of all time. I had this calculator in college. It's one of HP's calculators that uses RPN, reverse Polish notation. Do people here generally know what reverse Polish notation looks like? So briefly, it means that instead of doing something like 2 plus 2, you do postfix notation like 2, 2 plus. It turns out that it's actually much easier to parse, for example. So one of the smartest people with whom I work sat down to figure out what the new query language for the system was going to be. And he built a query language that is incredibly powerful to allow us to do a whole lot of complex queries, and at the same time made it kind of hard to do a whole bunch of simple queries. We've worked on that. So here's an example of one query that's relatively simple. So what you've got here is Q equals, so the query, NF region US West 1 equals, so there's the RPN, NF app employee info equals, and, so you're ending these two conditions, And then you have name, employee info underscore API equals, and. So you're ending now the result of these three conditions. And then basically the sum operation. You're saying that the end time should be now minus 5 minutes. So show me everything up to the last 5 minutes. And the start time should be end time minus 3 hours. So basically it's a 3-hour graph. And what you get is a nice little graph of activity on this employee info application. So this is relatively easy and accessible, and you can very easily look at your data, for example, on a per zone basis, because we send that tag for you by just adding a group by addition to this query. So that's very simple. You can see how accessible it is. I find that this is a good time to take a drink of water. Yeah. I can't actually tell you what this does, not because I'm not supposed to, but because there's like 15 or 20 people at Netflix who can actually understand this expression. Generally speaking, this is using a bunch of mathematical operators like double exponential smoothing to build a prediction line. That's the red line over here for expected traffic for one of our devices. I think this is actually the Nintendo 3DS, and then graphs the actual traffic on the same graph, and you can actually alert when those two lines cross. But this basically uses just a whole bunch of math magic and a whole bunch of really advanced Atlas query language skills. So that was another thing we built. Interestingly, by the way, when we built the system, we expected that our scaling issues were going to be around writes. People were going to send, tens and tens and tens of millions of metrics at us, and generally speaking, they weren't going to query for them, right? So there's no problem, just scale for writes. We were wrong. So, we built the system. Obviously, we have a whole bunch of graphs and dashboards that pull information out of the system. Our alerting platform is actually built tightly into the system, so any graph expression you use, you can also use as an alerting expression. It's exactly the same thing. But then we found that a whole bunch of people started using the system for a whole bunch of new things that we didn't expect. So for example, one of the people in my team built this automated canary analysis system that queries the system for a bunch of metrics every minute and tells you whether or not your canary currently running is doing well or not well. And it's actually integrated into our continuous deployment system. So the automated canary analysis tool will tell the deployment system to either scale up your canary ASG or potentially even take it out of traffic. Coburn, you want to raise your hand there? Okay, so Coburn Watson, right there, manages our performance team. And his team built this really interesting capacity analytics tool on our system that lets you actually look at things like your memory and CPU headroom on your system as a function of like the time of day by doing a whole bunch of analysis on metrics that they pull out of Atlas. We had a whole bunch of special projects running against our system. So for example, we recently talked about Scryer, our predictive autoscaling approach, which uses our system to pull a whole bunch of metrics and do mathematical magic on it. And amusingly, or tragically, depending on your point of view, BI. So BI is funny, right? Like we actually have an enterprise BI system that's pretty good, run by our enterprise BI people who are fantastic. But I remember talking to one of the client engineering managers about his use case for Atlas, and he said, listen, I send all of my data to our BI system, and any query that I want to predefine, I can always get the results of whenever I want to, and that's great. And any ad hoc query that I want to, run, I can do that and just wait 2 or 3 hours for the backend systems to crunch through the data and give me my results. But I don't need to, because with Atlas, I can do ad hoc queries as long as I send you all of my BI data, and you'll give me back my results within like 5 seconds. Our SLA is 99.99% of the time we're supposed to return your queries within 5 seconds. So we built an incredibly scalable system that lets you send any metrics you want. It also gives you back your metrics really, really quickly. And then it turns out that everybody who wants something like that, even not just for operational purposes, ends up using your system. We are definitely popular, mostly for the right reasons, but not always. So what does ridiculous read volume really mean? That's kind of a tall claim. So this is a graph of read activity on our system over 1 day. If you can't read the numbers, even from the front row, we're averaging about 60 million data points per second queried from the system across like every part of the day. So at the trough, we get down to about actually 32 million data points per second. At peak, you can see that we have a spike here up to about 150 million data points per second. We're averaging 60. And that's awesome, right? That's like big, except that that's only one day. So let's look at 3 days. The average is still around 60 million data points per second, but we go up to about 600 million data points per second queried. This is, we may have had a production emergency or something or some sort of batch operation that just decided to get a whole bunch of data from us. And that's awesome, but wait, there's more. This is our 5-day graph. The top number in this graph on the left side is 2.8 G. G is for, well, giga. So yeah, we're getting up to about 2.8 billion data points per second queried doing these 3 spikes that we see here. So that's a lot. How did we get this done? So this is the first draft of the system. What we have is, by the way, the people on your left side of the room, do you see my laser pointer? Okay, good. So we have the global endpoint. I talked about that earlier, the regional endpoint, and a bunch of back-end servers here. Let's say we have a client instance, a publish cluster, Amazon S3, and a puller cluster. So generally speaking, the vast majority of our metrics are actually sent in from applications that just push them to the publish cluster. Our puller cluster does things like SNMP polling, health check polling, all of that stuff, and then sends metrics into the publish cluster. Then the publish cluster simply sends the metric to the sharded backend instances, and also takes a whole bunch of those metrics, bundles them up into one big file, and puts it up in S3. So there you go. Problem solved. It's all great. And I did this in 24 minutes. We can all go drinking, right? Well, so it turns out there's a few problems here, and largely they're around speed, because speed is hard. And well, speed at volume is even harder. And we looked at ways of solving this problem. We looked at spinning disks, for example, and we looked at using, for our backend systems, Cassandra with SSD instances. And we did the math, and it was going to take us something like 700 SSD instances back about a year or so ago when Amazon was like, you're a special customer, so we'll give you 9. And that was just not going to work because it was also going to cost us like a lot of money. And my boss was looking sort of grim. So we decided that memory was the way to go. And so what we did was we basically built a system where the metrics for querying are stored in memory on a whole bunch of M2.4XL instances. For those of you not familiar with M2.4XLs, really? They're 64 gig instances. They're nice, sort of like they're one of the main fleet products for Amazon. It's worth noting that this is operational data, and that means 2 things. One, people really want it available fast. In fact, it's kind of funny, right? Because when there's a problem, you're going to see a whole bunch of people flocking to your telemetry data to bring up dashboards. So there's more activity. And this is exactly the time when you don't want to see degradation under load. So generally speaking, the higher the load on our system, the more impatient people are. The other thing that's worth noting is that operations people, generally speaking, have short memories. Also, operations people, generally speaking, have short memories. So that means that we don't necessarily need to look at data from like a month ago or 3 months ago. We generally care about what's happening right now and maybe what happened like last week for some higher level metrics. But the problem is that we basically did the math. And in order to support the metric volume that we had, we were going to need to have about 20,160 M2.4XLs. Using Amazon's public pricing, it was going to cost us about $32 million in upfront reservation fees, and then an ongoing $8 million a month per region with no redundancy. And that's a lot of money. So that didn't sound so good. And we were just looking at this problem, trying to figure out if there was a way we could, reduce the metric load. You like that? Yeah. So here's the thing. Our granularity is actually 2-dimensional. On one dimension, we have tags, and however many tags you have. And on the other dimension, we have step size, or the time buckets. So we typically use 1-minute time buckets, but we could use bigger time buckets. So it actually makes sense to reduce on either dimension, depending on your use cases. And some tags actually make sense for really rapid reduction. So for example, Hystrix, our dependency command library, sends a whole bunch of metrics that are not all that useful after about like an hour. So we can call them pretty quickly. The other one is the nf.node tag, which is the name of the instance that sent the metrics. So we bring up thousands of instances a day. We take down thousands of instances a day. That means that the average lifespan of a node in our environment, the average lifetime of an instance in our environment is like a day or two, at most, generally speaking. So that means that we don't actually need to keep instance-level metrics for all that long. Now, in some cases, we can even keep the shorter time. So for example, VHS, the viewing history service, is the application that tells us what our clients are doing. So VHS will tell us how many Windows 8 devices, for example, started streaming a minute ago. Well, we don't actually need to ever pretty much report how many Windows 8 devices told us that they started streaming to that VHS server versus that VHS server. So that kind of business data, we can actually just remove the instance tag dimension very quickly. On the flip side of that, our database engineering team is rightfully very proud because they actually now use Chaos Monkey to terminate their stateful database systems, just like everybody else at Netflix. But even doing that, their instances tend to stick around much longer than everybody else. So for them, they actually really like having instance-level data longer than everybody else. So here's what we did. We figured that for a series of values, we would reduce it to minimum, maximum, total, and count. Here's an example of that. Let's say you have 3, 5, 9, 14, and 20. We would then reduce that to 3, 20, 51, and 5. It's worth noting that we've just reduced a series of 5 numbers to 4 numbers, which is not actually a huge win, which is why we don't reduce to 5-minute buckets, because we would then basically just be going from 5 numbers to 4. The reduction that we do is on dimensions that have a much greater number of values. So for example, going from 1 minute to 1 hour takes you from 60 values to 4 values, which is about a 15x improvement. The nice thing about this system is it allows for a sense of scale because you know the minimum and the maximum. And by keeping the total and the count, you can very easily do further reduction without loss of precision. Whereas if you were keeping, for example, the average, you'd have a harder time doing that. So, by the way, when I was creating this presentation, I was looking on Flickr for Creative Commons licensed pictures. And part of the fun of this was figuring out what pictures come up when you search, for example, for policy. This is the picture that comes up for policy. I have no idea what it means. So we built this policy-driven system that allows us to basically take 4 possible actions depending on the time horizon and metric and other metric metadata. You can preserve the metric in the visible system. You can just drop the metric, so we're not going to have it available. You can consolidate the metric, which basically means going from one time bucket size to another. So for example, from 1 minute to 60. And you can roll up the metric. So you can basically take out a given tag and just show a summary for all the values for that given tag. Here's a quick example of a policy. You can see operations here is a drop operation. And the query here, for those of you who've been paying attention, you'll see that we're actually using the same query format across our entire system. So this is app API equals, class is in this list, and so we'll drop metrics that fit this pattern. And then for everything else, we will roll up based on NF node, device, and NF country. So the way this ends up looking now is everything remains the same, generally speaking, except that the EMR driver takes those big S3 data files, pumps them through EMR to do some reduction based on the policy, and then sends them to new clusters behind the regional endpoint. So you now see actually that we have 4 clusters. The first cluster is the 6-hour cluster. So it keeps data only for the last 6 hours, and it's fed directly from the publish cluster. We also have the 4-day cluster, which includes data for the last 4 days, 18-day cluster, and historical cluster. The further back you go, the more we've reduced the metrics. But that also means, actually, that when people want some sort of special access to metrics that we've already put in S3 and are no longer available in these clusters, they just ask us to add a new policy as an ad hoc basis, and we can bring up new ad hoc clusters for their requests. This has worked reasonably well for us, actually. It means that we can continue to do indefinite storage in Amazon S3. It also means that we don't really have to worry about making the wrong decisions about metric aggregation. So that means that, for example, about 2 months ago, we sent an email to our users saying, hey, listen, any metric that hasn't been queried for like more than 2 weeks, we're just not going to have visible. And if we didn't notice something that you want, no problem, just let us know. We'll get it back in there in a matter of 2 or 3 hours, and we'll just keep it there. So we don't have to worry about, oh, we made that decision to roll metrics up, and damn, now we can never get back that granularity. It also means that we can do high granularity for special days, and I find this really awesome. So we have special days in the year. Thanksgiving is one of them, Christmas Day, the Oscars, Super Bowl. All of those days have very special traffic patterns. They're very different from other days in the week. And most systems I've ever seen that did metric aggregation did it sort of in a continuous way. So whatever your granularity 364 days ago was, you can't have higher granularity 365 days ago. But since this is all policy-driven, we can do arbitrary granularity for any special day or even special time that we want. It's automated for regular operations because we love the idea of applied laziness. And it's not in the critical path for visibility SLA. That's really important to us, right? So EMR could go down and not be available, and you'll still have access to the last 6 hours of data within 5 minutes of sending it to us. The other thing that we actually hadn't considered before we built this is that it helps us firewall accidental metric explosions. So here's what I mean by that. As I mentioned, developers can create any tag keys and values that they want for their metrics. We have had occasions when a developer, mostly as a mistake, decides to add a tag key, client IP, tag value, the IP address of a given client that sent the request in. There are a lot of IP addresses. And suddenly you find out that you've gone from, like, let's say 10 metrics to 10 million metrics very quickly. When we find these problems, we can actually put in additional policies in our EMR system to make sure that those tags get culled out of the system before they go into the historical clusters. So overall, this has been a huge efficiency gain. How huge was it, Roy? Coburn, I thought you were going to ask that question. So here's what I'm talking about when I talk about huge. This is the sizing for our clusters. And for each cluster, I'm giving you the time horizon, so how long it keeps data for, the number of instances in the cluster. These are all M24 XLs. That's the size, and the calculated instances per hour, and then the % reduction. So our 6-hour cluster, which doesn't use EMR and is therefore the reference point for this, has, when I looked at it about 3 weeks ago, 600 M24 XLs, which 600 divided by 6 is not hard math. It's 100 instances per hour. It's expensive. Our 4-day cluster has 512 instances, which if you do the math, oh, that's interesting. Amazon reformatted my slide to drop decimals. I'm a big fan of precision, as you might have noticed. So it's 5.33 instances per hour. And I demand to say that it's 5.33 instances per hour. And it's about a 95% reduction. It's actually 94.7% reduction, but let's not quibble. Our 18-day cluster has 180 instances, which turn out to be 0 instances per hour. It's actually, I believe, 99. Well, anyway, our history. So I will tell you that I know for a fact that our history cluster, which has 12 instances in it, translates to 99.996% reduction in size per hour compared to our to our 6-hour cluster. So where do we go from here? Well, for one thing, we know that because we're big fans of applied laziness, we want to stop dealing with those special requests that our customers send us. We get about 3 or 5 of those per month, and they're not that big of a deal, but we'd prefer to not deal with them. So we're going to build a self-service model to deal with that. The other thing that we want to look at is some different instance types. These didn't really exist well, they didn't exist quite as easily back when we started looking at this. So CR18XLs have 240 gigs of memory, and they're like twice the cost or so of M24s. So this could end up being like a 2x reduction in cost. High 1.4XLs have 2 terabytes of SSD storage, which is super, super attractive to us. So we're starting to look at that as well. But fundamentally also we know that while people ask for metrics a lot, they're not actually asking for a lot of metrics. So there are metrics that are asked for much more often than others. And building a system where the metrics that are not asked for very often are on slower storage will probably allow us the next quantum shift in the system. So metrics growth. I showed you how things were when we started working on the system. And we had 2, 2.5, 10, and this is where it stops. OK. So we got to 15, and then things sort of went a little crazy. So by January of this year, we were hitting about 90 million metrics per minute. By May, we hit about 212. We hit 728 million metrics back in October, a month ago. And our current predictions, yeah, so that's 1,200 or 1.2 billion metrics that we expect to hit by January. And at this point, we know that our system will be able to actually accommodate that and not, in fact, bankrupt us. So speaking of bankrupting us in costs, this is actually a graph of the cost per metric per day in our old system. Don't worry about the scale on the left. It's worth noting before we talk about that, actually, that our priorities are speed of innovation first, availability, and then cost. When we built the new system, we did not intend to come up with a new system that was going to be cheaper. We wanted to focus on migrating our telemetry platform to the cloud. We wanted to make sure that it could support a whole bunch of extra features, like being able to show us per zone traffic. And we wanted it to be able to scale to huge, huge levels. So given that, the green line is the cost per metric per day on the new system. We actually managed to hit about a 90% reduction in cost per metric per day in the new system versus the old system, while scaling higher, while giving you more features, while being cloud native. So really, this is the story of how Netflix used EMR, an Amazon product, to not pay an additional $16 million or so per month to Amazon. At the same time as growing a ridiculously huge monitoring system that serves our needs on a day-by-day and second-by-second basis. That's all I've got. You can ask questions, or you can go get some beer. What would you like to do?